Hi there, welcome back to our course, Advanced Quantum Mechanics. This is lecture 31. Let's remember some basic definitions. Pure versus mixed states. And once we've done that, we'll do unentangled versus entangled states, just to make sure we don't mix them up. So the definition here is that a pure state is when we know the state. Pure state means we know the state that the system is in. So say psi is the state. And then if we choose a basis, then we can write that psi is equal to sum over n, and then we have coefficients psi n, bn. The psi n form the wave function. Now, what's the density matrix of a pure state? You see, for a pure state, we don't really need to use the notation of a density matrix. We can if we want to, but we don't have to, because for a pure state, we can just write psi. But we can also use its density matrix. So it has this density matrix. Namely, rho hat is equal to psi, psi. Okay. What does that mean in a basis? Well, this means it is the sum over n and m. If we just plug that stuff in here, then we get that this is psi n, psi star m, and then bn, bm. So that's how it looks like in a basis. And then remember, we have that rho hat dagger is rho hat. This is a self-adjoint operator, the density operator. And we have that the trace of rho hat is equal to 1. All of that is quite obvious. You know, you can just choose psi to be a basis vector, and then clearly the trace is just 1, because rho is in its eigenbasis simply the diagonal matrix, which has only one non-zero element on the diagonal, and that element is 1. Okay, now what does mixedness mean again? Definition. All other states are mixed. Now, i.e., they are of the form where we have rho hat is equal to sum over n and m, and then matrix elements rho n m, and then bn, bm. We still have that rho hat dagger equal to rho hat. Density matrices are always self-adjoint. The trace of the density matrix is always 1. Remember, this means that the sum of the probabilities has to add up to 1. And because it's a mixed state, it means there doesn't exist a basis so that rho hat actually factorizes in the form that a pure state would, which is in this way. So there doesn't exist a basis such that rho nm is equal to psi n, psi star m. Because if it were, right? If there was a basis in which these matrix elements took this form, this product form, then these would be the wave function of the pure state that our system is in. All right, so this is older stuff. This is about pure states versus mixed states. But now let's look at entangled versus unentangled states. So unentangled versus entangled states. Now, this is a notion that only makes sense if we have a composite system. So, only makes sense for composite systems AB. Very important. Now, case one. Assume that the state of the composite system of system AB is pure. So it's this pure state which is an element of the Hilbert space of system AB. Then what is its density matrix? From what we just said before, recalled before, we have that then therefore the density matrix of the system AB for this pure state is omega. Now we say, here's the definition. The state omega of the composite system of AB is called unentangled if there exists a psi in the Hilbert space of subsystem A and a state phi in the Hilbert space of subsystem B, so that omega is the tensor product of them. So that omega is equal to psi phi. Remember, we are not usually writing tensor product symbols anymore. And then the definition is that if this is not possible, then the state is called entangled. So otherwise, omega is a sum. So we have to write omega equal to sum over I, and then we have multiple states. And then, so if this sum has more than one term in it, right, then this is the case of otherwise, then we say, and we say omega is entangled. Now, that was all of that we've had before. Now, let's do case 2. In case 2, we assume that the state of the total system, AB, is mixed. So now, assume state rho hat AB is a mixed state. Now, what's the definition then? And now the definition is that we say that, well, first of all, let me just sketch something. Imagine that the two subsystems are in a state rho hat. I just give you the full definition right away. Okay, so we say that the system rho hat AB, the system with the state rho hat AB is unentangled. Well, if it is in a linear combination of unentangled states. So it is unentangled if it can be written in the form rho hat AB equal to the sum over, and then we have a probability distribution of numbers Wi, and then rho hat AI tensor rho hat BI, where the omega I are positive numbers and the omega I have to add up to 1. So what this means is that we say that a density matrix of a composite system is unentangled or separable. So this is the so-called separable case. Is separable if the density matrix is understandable as a probability distribution of obviously unentangled states. You see, if we have a density matrix here and a density matrix there, then these two are just independent systems. And if we just have a probability distribution running over those, then it's still just an ensemble of unentangled systems. So therefore, the whole thing is unentangled or separable. And then, of course, otherwise, we say that it's an entangled state. Otherwise, so if the density matrix of the total system cannot be written in this form, otherwise rho hat AB is called entangled. Now, we will not further pursue this case. And the reason is that, well, there are two reasons. One is it's getting really messy if you look at a composite system that's in a mixed state. But it's also, strictly speaking, never necessary to look at composite systems that are in mixed states. In principle, you can always choose by the dilation theorem that we covered earlier. If you have a system A, you can always choose to combine it with a system B in a bigger Heisenberg cut, such that the total system AB is in a pure state. And that is what we will, for the rest of this course, always assume. We will assume that when we consider composite systems, the total system is in a pure state. The terminology that is used in this context is that if a system A is in a mixed state, then we can always purify it by changing the Heisenberg cut to a bigger system AB. So we say then that B purifies A. So we say here, remark, given a system A in a mixed state, there exists a purifying system B, and the whole point here is I want to explain the word purifying system B, so that rho hat AB is pure. Therefore, we will now always assume AB, the system AB, to be pure. Of course, experimentalists may run into situations where they will have to consider composite systems that are mixed, but for theoreticians, most of the time we get away with that simpler case. All right. What is it we found out about the relationship between purity and mixedness on one hand and entanglement or unentanglement on the other hand? Let me remind you of the basics here, because it's so important. So when we have the situation of a system A and a system B, and then we draw the Heisenberg cut around both of them and call that system AB. Then system AB is in a state rho hat AB, and then system A is in a state that we may call rho hat A, and system B is in a state rho hat B. And we found now assume, first of all, again, I'm just writing it to make sure that we are not overlooking this. Assume that rho hat AB is pure. Okay, so we have that rho hat AB is equal to omega. Well, then our finding was this: if omega is unentangled, and that is to say, i.e., omega is equal to some psi tensor some phi, then this implies and is implied by the following fact. Namely, that rho hat A is pure, namely rho hat A is equal to psi psi, and rho hat B is pure, namely rho hat B is equal to phi. And the converse is also true. And the converse is true, namely, again, remember, assume rho hat AB is pure. I have to say that because our conclusions are simply not true if the system AB is not in a pure state. But we're assuming it's in a pure state. Then what we have is that if omega is entangled, so let me say, i.e., we have that omega is the sum over such vectors in the two Hilbert spaces. And this sum runs over more than one term, because if it's just one term, then we have unentanglement. Then this is implied by and implies that rho hat A is mixed. Namely, what is rho hat A? Rho hat A is equal to the trace over B of omega omega. And also the state of the second subsystem is mixed. And you can, of course, remember what the density matrix is, trace over A of omega omega. Remember, this is an operator in the Hilbert space of system AB, but after we've done the trace over A, this whole trace is still an operator, but an operator on the Hilbert space of system B. Now, remember how we calculated that? What is this? Let's just spell it out for rho B, for example. It would be the same calculation for rho A. So, for example, if we want to calculate what is rho hat B, how do we evaluate this trace here, right? So this is equal to the trace over A of omega omega, so bracket. This is the trace over Hilbert space A, and then, well, remember what omega is, it's this. So we have here the sum over I and j, and then psi I, phi I, and psi j, phi j. I was just subbing in the omega into that equation down here. And now we have to evaluate that. So what is this then? Well, this is then what we obtain when we evaluate that trace. How do we evaluate that trace? Remember, we have to choose a basis, arbitrary, but we have to choose a basis in the Hilbert space of system A. And then we have to put these basis vectors left and right so that we end up summing over the diagonal there. So what we have here is that this is the sum over all n, and then we choose basis vectors here. So we have here an, and then, well, we also have the sum over the ij, so let me write that here, I and j. So we have the an here, and then in here we have this thing. We have the psi I, phi I, psi j, and phi j. And here we have the an again, right? Because we're forming the trace over the Hilbert space of system A. And let's say these are basis vectors in system A. So these guys are elements of the Hilbert space of system A. Right, now how does this evaluate? Remember that this vector here is an element of, well, the dual, because it's a Bragg vector, it's an element of the dual of the Hilbert space of system A. So H, A, star, right? It's the dual of that space. And that thing is in the Hilbert space of A. And that thing here, this Bragg vector, is in the Hilbert space A star. It's a dual, right? And so we see that this one will eat up that one, because this is dual vector to that. This one will eat up this one, and we are left with the phi. So what we have is sum over n I j, and then we have the following numbers: an, psi I, that's a number, right? And then from here we have psi j an, and then here we have left over the phi I and phi j. Now, where does this thing live? Well, remember, this is an operator on the Hilbert space of the system AB. After we trace over system A, we are left with an operator of a system of the Hilbert space of system B. That's what we have. This is numbers, and here we have an operator that acts on the Hilbert space of system B, because this is, you know, a dual vector in this is in the Hilbert space of system B, dual, and this is in the Hilbert space of system B, right? So this is an operator there. Okay. Right. And now we can flip these two around, right? So this is then the sum over n and I and j, and then we have here psi j an and an psi I and phi I phi j. This is a resolution of the identity here, so we just end up with the sum over I and j, and then these numbers, psi j, psi I, those overlaps, and then here we have phi I, phi j. All right, so this was just to give a flavor of how you would calculate the density matrix of a subsystem, right? So what we just did is we said, given the density matrix of the full system, a pure state, by the way, then this, what we just did was to calculate the density matrix of rho B, the density matrix rho B, and similarly we could then calculate the density matrix rho A. All right, now in practice, okay, let me just summarize an important conclusion that we had drawn, namely that if the state of the total system is entangled, remember, if this state is an entangled state, so if A and B are entangled, then rho A is mixed and rho B is mixed. And it works also the other way around. If these guys are, if the total state is unentangled, then these states of the subsystems are pure. So entanglement in the big system, in the supersystem, means mixedness of the subsystems. Okay, so purity of the subsystems goes hand in hand with unentanglement of the supersystem, and mixedness of the subsystems is an expression of there being entanglement in the supersystem. So mixedness here and there means the whole thing is entangled. Keep that in mind. Entanglement in the big system means mixedness of the small systems. No entanglement in the big system means that the subsystems are pure. But in practice, we want to know more than just the binary information of whether or not there is entanglement. No. We need to know how much entanglement is there. How much are systems A and B entangled in this big system AB? How do we measure that? Now, in order to measure that, we can make use of the fact that entanglement in the big system means mixedness in the subsystems. And we do know how to measure mixedness. Remember, we can use the Entanglement Entropy to measure mixedness. This suggests that in order to quantify how much systems A and B are entangled with each other, we can simply measure how much system A is mixed. If it's pure, for example, then we know it's not entangled with A. If it's mixed, it's entangled with B. The more mixed A is, the more we say that it is entangled with B. Okay, so let's do this systematically. How to determine or quantify, determine how much A and B are entangled. Now the idea is use a measure of how mixed A is. So we use the following definition. Assume rho hat AB is pure, right? Remember, we always make that assumption. I just always write it there so that there's no misunderstanding. Then we determine the amount of entanglement between A and B as the von Neumann entropy of subsystem A. So you have a composite system AB, and you wonder how much are A and B entangled with each other? Well, just measure or calculate the entanglement entropy of subsystem A. If the entanglement entropy is 0, then we know that they're not entangled. The higher the entanglement entropy, the more they are entangled. So what we say is that amount of entanglement between A and B is S, the von Neumann entropy of rho hat of system A, which, if you remember, is minus the trace over system A of the density matrix of system A, and then the logarithm of the density matrix of system A. And here, the density matrix of system A, remember, is obtained by tracing over system B the density matrix of system AB, which is the trace over B of omega. So this is the most popular method, the most useful method for determining how much two subsystems A and B are entangled with each other. Namely, you take the pure state of the total system and trace it over B to obtain the density matrix of subsystem A. Then you plug that into this formula for the von Neumann entropy. And that gives you some number which is 0 if and only if the density matrix is a pure state density matrix, as we know from previously in the course. And the more rho is mixed, and therefore the more the two systems are entangled, the larger is the entanglement entropy. So all of that is good, but you may have noticed that there's a problem. There's a potential problem. Potential problem. Why not use the von Neumann entropy of subsystem B? Shouldn't this thing be democratic? If we have a system composed of two subsystems A and B, and we are asking how much are A and B entangled, why would we single out system A and calculate the entanglement entropy of its density matrix rather than the entanglement entropy, or the, sorry, it's called the entanglement entropy, but it's here the von Neumann entropy. Why not just calculate the von Neumann entropy of system B? For the definition to make sense, it should not depend on whether we calculate it using subsystem A or subsystem B. And it would seem pretty unlikely that the entanglement entropy, that the von Neumann entropy of system A is the same as the von Neumann entropy of system B. You may wonder why. Why is that unlikely? Well, just consider that you could take a combined system, a composite system, which consists of two subsystems that are of vastly different size. For example, one subsystem might be a hydrogen atom, and the other subsystem might be an elephant. Then the total system is an elephant and plus a hydrogen atom. Then clearly the density matrix of the elephant might be rather more complicated than the density matrix of the hydrogen atom, one would think, right? You could even have one subsystem that has only a two-dimensional Hilbert space, whereas the other one might have an infinite dimensional Hilbert space. So generally those density matrices might be of different sizes, right? So this might be a density matrix acting on a Hilbert space of infinite dimension. This might be a density matrix acting on a Hilbert space on finite dimension. So why does it make sense to single out system A? Well, the answer is it doesn't make sense. You could as well single out the density matrix of system B, calculate its von Neumann entropy, and then declare it to be the entanglement entropy, and you would get the exact same number. In spite of that example of the elephant and the hydrogen atom, it's still true that, in fact, and here's a proposition. The von Neumann entropy of subsystem A is the von Neumann entropy of subsystem B, no matter how big or small each one of them is. Now, that means, therefore, the entanglement entropy is well defined, and by that we mean unique, either as, S of rho hat A, or S of rho hat B. It doesn't matter because it's the same number. This is a very important statement also for practical purposes. If you want to know, if you want to calculate how much two systems are entangled with each other, and one of the two systems is way bigger than the other, then this proposition tells you, well, just calculate the von Neumann entropy of the smaller system's density matrix, because you get the same number as if you calculated it for the bigger systems. It doesn't matter. So you can choose which one of the two to calculate, you always get the same answer. Now, what about the proof? while the proof is a little bit tedious and it would cost us too much time. I give you the proof in all detail in the lecture notes. For now, let me just show you what the strategy is. So proof strategy. Proof strategy consists of this. First of all, you show that if lambda is a non-zero eigenvalue of rho hat A, then lambda is well, of course, it's still, still non-zero, is also eigenvalue of rho hat B. Of course, they have different eigenvectors, but each non-zero eigenvalue of the density matrix of one subsystem is also eigenvalue of the density matrix of the other subsystem. And one can show that this even conserves degeneracies. So if one eigenvalue is 27-fold degenerate, then the other subsystem has that same eigenvalue also 27-fold degenerate. So this preserves also degeneracy. Now, secondly then, the density, the Von-Neumann entropy of our density matrix depends only on the eigenvalues of rho hat A that are non-zero. Remember that the Von-Neumann entropy of a density matrix such as rho A is minus, in the eigenbasis, it is minus sum over, and then you have the eigenvalues, rho n, sum over n, rho n, ln rho n, and whenever an eigenvalue is zero, it's not going to contribute to the entropy. Therefore, since the spectra of rho A and rho B are the same, except possibly for eigenvalue 0, we have that the Von-Neumann entropies that are calculated from those spectra have to be the same. So therefore, the Von-Neumann entropy of rho hat A is equal to the Von-Neumann entropy of rho hat B. Okay, this is what needed to be shown. And what is a little bit tedious is to prove that if lambda is a non-zero eigenvalue of the density matrix of subsystem A, then lambda is also an eigenvalue of subsystem B. But I gave you the proof in the lecture notes. Now, now we have a method for calculating how much two subsystems are entangled with each other. Namely, we just calculate how mixed one of those subsystems is by calculating how large its Von-Neumann entropy is. And the Von-Neumann entropy has a cool meaning because, remember, it has an information theoretic meaning. It quantifies the number of questions that needs to be asked in order to remove the ignorance. Right? If you have a density matrix, you don't know which state it is. And the entropy tells you how many questions with at most n, with n outcomes you would have to ask to specify exactly what the state is that we are in, where n is the basis of the logarithm. And in our case, we choose it to be e, so we are measuring information in, not in bits, but in nuts. The upshot of this is the entanglement entropy, defined as the von Neumann entropy of any one of the two subsystems, is a very useful measure of how much two subsystems are entangled with each other. But it has a disadvantage. And that disadvantage is that the von Neumann entropy is hard to calculate. Because what you have to do is, you have to take the pure state of the total system, then trace over B to get the density matrix of a subsystem. And then you're not done at all. At this point, you have to diagonalize that matrix, because only then can you make sense of the logarithm of it, namely by taking the logarithm of each one of its matrix elements, right, in the eigenbases. So you have to diagonalize the density matrix, then take the logarithm, and then multiply with the density matrix, and then take the trace of that. Doable, but somewhat tedious, especially if rho is in an infinite dimensional Hilbert space, because then diagonalization can be a hard problem. Now, there is another way in which you can quantify how much two subsystems are entangled, and that other way doesn't require that you diagonalize the density matrix. So here is a simpler method to determine how much a subsystem, let's say A, is mixed, and therefore how much A and B are entangled. Now, how does that work? Well, here, how? Here's the definition. We use the notion of purity. Definition, the purity of a density matrix rho hat, and in our case we will apply it to rho hat A, but the definition is general for all density matrices, is defined as P of rho hat equal to the trace of rho hat. Well, that would be trivial, right? Because the trace of every density matrix is 1. But we are taking the trace of the square of the density matrix here. That may not be 1. Now, clearly, this is way easier to calculate than the von Neumann entropy, because instead of having to diagonalize a matrix, we only have to square it. That's way easier. And then once we've squared it, no more logarithms or anything, we just square it, and then we take the trace of it. So this is much easier. Now, what are the properties? Well, let's see. Assume that rho hat is pure. So we have rho hat is equal to some psi, right? Then we have that rho hat squared is equal to, well, psi. This is 1, so it is equal to rho hat. So therefore, when rho hat is pure, we have that the purity of rho hat is equal to the trace of rho hat squared, which is then the trace of rho hat, which we know is 1. So if a state is pure, then the trace of the square of the density matrix is 1. So therefore the purity is 1 if the state is, so if rho is pure, if rho hat is pure, then the purity measure has the value 1. Okay, now let us write down for the generic case where it may be mixed, let us write it down in a basis. So in a basis, well, in the eigenbasis, let's choose the eigenbasis for convenience. In the eigenbasis of rho hat, we have that P of rho hat is equal to the sum over all n, and then, well, we take the square of the density matrix, which has on its diagonal the elements rho n. We have to square them, and then we have to sum them up. So this is sum over the rho n squared. So the rho n are the eigenvalues of the density matrix. So the probabilities for finding the system in the state n, the nth state, the nth basis vector of the eigenbasis of our rho hat. Okay, so that's how that looks like there. Now, if rho hat is not pure, then, so if it's not pure, then we have that the sum over all n of rho n is of course 1. That's true for every density matrix. And we have that the rho n are smaller than 1, right? That's because one of them would have to be equal 1 and all the others would have to be 0 for the state to be pure. So if the state is not pure, then all the states have probabilities strictly smaller than 1 for all n. But then we have that rho n squared must be smaller than rho n, right? Any number, any positive number that's smaller than 1 gets smaller when squared. So we have that the rho n squared are smaller than the rho n for all n. But this means that the sum over all n of the rho n squared must be smaller than the sum over all n of the rho n. But this is the trace, it's just 1. So therefore we have that if rho hat is not pure, then the purity measure is smaller than 1. Okay, so we have, so if rho hat is not pure, then the purity measure of rho hat, which is the trace of rho hat squared, is strictly smaller than 1. Now, that's good, and we can use this as a measure of how mixed the state is, or how pure or how impure it is. Because obviously, the more we have, the more rho n's we have that are non-zero, the smaller the rho n's have to be. But the smaller they are, the more is the difference, the larger is the difference between the rho n squared and the rho n. And therefore, the larger is the difference between the purity measure and 1. So the more mixed the state is, the smaller is our purity measure here. So we can use P as a measure of purity. with the maximum purity being achieved for the value 1. So, so far in conclusion, therefore, we can use P of rho hat A to determine how mixed system A is, and therefore how entangled A and B are. Now, could we have chosen to use the purity of the density matrix of rho B? Yes, we could. It would have gotten us the same value. Notice this is the same issue that we addressed with the entanglement entropy too. The von Neumann entropy of one subsystem matches the von Neumann entropy of the other subsystem. And here too, notice we have that the purity of system rho hat A is equal to the purity of system rho hat B. Why? Well, the spectra, well, we have that the spectrum of rho hat A, let me put a prime here, is equal to the spectrum prime of rho hat B. We know that from before when we studied the von Neumann entropy, namely that rho hat A has the same eigenvalues, the same non-zero eigenvalues as rho hat B. And it's only the non-zero eigenvalues which go into the calculation here. See, when you sum up the sum of the eigenvalues, the zero eigenvalues don't contribute. You could have a billion of them, they were not going to change the purity measure. And the non-zero eigenvalues are the same. So, so this is except for zero eigenvalue. So therefore, it is a well-defined measure. The purity can be used to measure the purity of a state, just like the von Neumann entropy can be used to measure the purity of a state. But both of them can also be used to measure or to quantify or to put a number to how much two subsystems are entangled with each other. And the purity is usually the quicker way of doing things. It also gives you a good indication for how entangled two systems are, but it's not as reliable. It doesn't have as nice properties as the entanglement property has. It's just way easier to calculate. In fact, in case you're interested, we don't have time to get into this, but it's clear that the purity has a generalization. You see, we took here, for our purposes, the purity to be defined in this way. The purity of the density matrix is a trace of the density matrix to some power. We could choose another power. We could take the power to the fourth or to the nth. And so we get a whole family of purities there. And you may wonder, what's the purpose of that? Well, it turns out it is quite useful, because actually when you look at the family of all purities with an n up there, then there is a certain limit where the purity has this power going to 1, where if you divide by something suitable, because if you set it to 1, then the trace of the density matrix is 1. But there's a limit that you can take such that you obtain the von Neumann entropy. So it turns out that in the family of purity measures of density matrices, where the family is defined by a power up here, there is a certain limiting case which shows the fundamental entropy as being a special case of the purity. All right, so far what we have done is we have found that when we have a, let me just demonstrate it again. So we have that if we have a subsystem A and a subsystem B, and we declare them together to be a system AB, then if this system here is in a pure state omega, and that's its density matrix, then if this is an entangled state, those two subsystems are going to be mixed. If the omega state is unentangled, then the two subsystems are pure states, are in pure states. And it's not just entangled or not entangled. There are degrees of entanglement. And we identify these degrees of entanglement with degrees of being mixed of the A and the B. And we had two measures of mixedness. One of them was the purity that we just did, the sum of the squares of the eigenvalues of the density matrix. And the other measure was the phenomenon entropy. Now the phenomenon entropy and the purity can be calculated for A or for B, and they come out always the same way, because the density matrix of system A and the density matrix of system B have the same spectrum, the same non-zero eigenvalues. In the zero eigenvalues, they could differ in the sense that they might be very differently degenerate. But it doesn't matter in the calculation of the phenomenon entropy or of the purity. And this last point I want to make is the fact that the density matrix of A and the density matrix of B may differ in the number of times that zero occurs as an eigenvalue. This explains why even a hydrogen atom and an elephant can have the same phenomenon entropy and can have the same purity. See, the density matrix of a smaller system, such as a hydrogen atom, in principle has few eigenvalues. If these were finite dimensional systems, this would be strictly true. It's a smaller density matrix, and the other one has a bigger density matrix, like the elephant has a bigger density matrix. But what we showed is that the non-zero eigenvalues are the same, and they occur the same number of times in both subsystems. But the eigenvalue zero can occur many more times for one system than for the other. And that's what's happening there. If system B is huge and system A is small, then the density matrix of system B is just going to be the same as the density matrix of A, except lots of more zeros in it on the diagonal when you diagonalize it. All right. Okay, so far we have studied the statics of a composite system. How does a composite system decompose into its subsystems? What happens if we move the Heisenberg cut, right? So that's what we did, static. What we have not studied so far is what happens when you let two systems that are initially not entangled, so A and B are both in pure states, we let them interact now. Then they become entangled. And that process of them becoming entangled means that each one of them becomes mixed. And that can also be viewed as a measurement process. And interactions are measurements. Interactions entangle, interactions make pure state mixed, and that's what we will do in the next lecture. Okay, this is as far as we got today. See you then.